Um, Hi, my name is Eva, and I'm a PhD student at the University of Leeds. I'm in my first year, and I'm using radar satellite data to better understand volcanic activity at volcanoes in Southeast Asia. But that's not the topic for today. So today I'll be talking to you about how we can use satellites for volcano monitoring. And this is a quick overview now about my talk. I thought about I'd be starting with talking a bit about orbits and the satellite revisit time, and then give you an overview about the Copernicus satellite missions, because they're a freely available satellite imagery source, and so every one of us could actually use that. So I thought that would be exciting to look into. And then I'll talk to you about volcanic hazards and what kind of monitoring tools we can actually use to observe them, and then go further into which satellites are actually relevant for volcanic monitoring, and give you some examples of the satellites and some imagery of that, and yeah, exactly show you what we can extract out of this satellite imagery. And finally, I'll show you a quick exercise of how we could use, how you at home could also use optical satellite imagery to look at lava flows, which is really exciting. So let's get started with the orbits. So an orbit, so basically, every object that travels around the planet is called a satellite, and each complete journey of these satellites around the Earth is an orbit, and it's basically a curved path around the Earth, which is caused due to gravity. And we do actually have this one natural satellite which is orbiting around the Earth, and that's the Moon, as you probably know already. But since October 1957, many thousands of artificial satellites have actually been placed into orbits around the Earth in order to help us better understand and analyze the Earth. And there are actually many different orbits, which is used for research or other applications, depends on what the satellite is actually designed to achieve. So if we look at the first one, that's the geostationary orbit, and this is, as the name says already, an orbit which is actually traveling at the same rate as the Earth, which means that it appears to be stationary to the Earth at a fixed point, and this is actually really useful for telecommunication or weather monitoring. And it's actually really far away from the Earth, so about 35,000 kilometers away from the Earth. We'll shortly see that that's way further away than other orbits, for example, are. So then we could use the low Earth orbit, LEO, which are it doesn't need to be around the equator as GEO before. It could be at any angle around the Earth. And this is about a distance from 1,000 kilometers away from the Earth, located usually. And this is mostly used for satellite imaging, or also the International Space Station is located there, because it's the closest to go to for astronauts, and it's a good position to take satellite images, because this means that the image resolution will then also be very high, because the position of the satellite is so close to the Earth itself. There are also other satellite orbits, like the medium Earth orbit, which is somewhere located between GEO and LEO, and this kind of orbits are usually used for the navigation system. So as soon as you get any kind of information on your phone regarding where you are, this kind of information is usually coming from those kind of satellites in the medium Earth orbit. And last but not least, the last one I'll talk to you about is the polar orbits and the sun synchronized orbits, so the SSO orbits. And these are very special in comparison to the other ones because they're synchronized to the sun, and this basically means that as a satellite located on this orbit is traveling around the globe, it will always be at the same latitude whenever it kind of like it's the second time on the circle, kind of, which means that it will always be, if it passes by Paris at 12 p.m., it will pass by Paris always at 12 p.m. So that's always the same time there, which is really important for research because you, if you look at some kind of volcano, for example, you would want to see the volcano always during the same time, so you don't have any shadows or anything which would change the situation. And the same comes also into play for when you want to look at cloud coverage, for example, because this is also quite often very, very daytime dependent. Yeah. So here I do have a quick animation for you, which will open up here. So that's the example of one of those Copernicus satellites. It's Sentinel-1. And this mission is actually consists of 2 satellites, and they are orbiting on the same orbit, the Earth, which basically means that they have a revisit time of a specific location on the Earth after exact 6 days, which means that one of those satellites itself would actually take 12 days to revisit one location. But since there are 2 satellites, we can actually see imagery of one specific location after 6 days, which is really exciting. So those are those Copernicus satellites I was just mentioning. These types, they are satellites by the which are operated by the European Space Agency, the ESA, and it consists of 7 satellites, or actually 6, which are in use. So Sentinel-5P is in space at the moment and is kind of like a preliminary one, and Sentinel-5 will be in space in the future, and then 5P won't be operating anymore. So if you look at all those satellite missions, they all have a different reason why they are for what they're used. So Sentinel-1 and 2 are used for land monitoring, and then Sentinel-3 and 6 are used for the ocean, seas, to look at the sea surface topography or temperature of the sea surface. And then Sentinel-5, 5P, and 4 are used for air quality measurements. I'll go into this a bit later on. So using satellites for in order to monitor volcanoes can be actually really, really crucial, because there are actually so many volcanoes on our globe. And I'll quickly open Google Earth for you. And as this is opening, there are around 1,500 potential active volcanoes on our globe, and about 500 of them have been active within historical times, so that people were actually able to observe them. And if you look at this globe, those are all historical but also ancient volcanoes. So it's actually our Earth is actually full of volcanic activity, and the most volcanic activity is actually seen around the Ring of Fire, which is this area around here. Here is kind of like the peninsula of Kamchatka in Russia, going down through Japan and the Philippines and Indonesia and Papua New Guinea here, and some islands in the Pacific, and then also the Andes and in South America and Central America and North America. So that's actually the most volcanic area on our globe. But there, as you can see, so many remote locations actually, so we can't really go to all of them and monitor the volcanoes with ground-based measurements. So therefore, actually satellites are really useful, and I'll come back to that in a bit. Also, I wanted to point out that you want to remember Etna, which I hope that most of you know, because like here we are in the UK, and that's Etna. Maybe some of you have seen that in some kind of holidays or so already. It had an eruption going on, and actually still is erupting at the moment. It's basically always kind of active in February and March this year, and we'll be looking at some imagery of this one later on in my presentation. So yeah, back to the presentation. So if we want to use satellites for volcano monitoring, we firstly need to consider what actually hazards there are and what kind of monitoring we could use in order to observe them. So there, as you can see on this left-hand side image, there are various hazards from lava flows to pyroclastic density flows, which are basically hot avalanches, including gases and very like volcanic material, which is rushing down the volcanic flank and is quite often very, very deadly, to lahars, which are which are basically can you actually, yeah, you can see my mouse, which are mud flows created through heavy rainfalls, for example. But it's also, or another hazard would be a dome, which is basically a very, very viscous lava, but it's not flowing down the flank as a normal lava flow. But since it's so viscous, it's kind of like building up to a dome-shaped form. Those are kind of like the hazards which show deposit at the volcano, and I'll come back to this in a bit too. But there are also hazards like emitted gases or emitted or like ash, which is being ejected throughout the eruption. So all those things we can actually look for when we want to monitor the volcano. And there on the right-hand side, you see a couple of tools which we could use to better understand this volcanic activity. And like there are many ground-based methods, like using seismometers to understand the earthquakes of the volcano, or GPS stations to know whether the volcano is moving, uplifting, or whether you can see uplift or subsidence. But actually what we're interested today is this remote sensing technique over here, the actual satellite remote sensing of volcanoes. So if you want to know now which of those satellites from the Copernicus satellite missions could be useful to for volcanic monitoring, I'll tell you, and we'll look in them more detailed now. So those 4 are not really relevant for us now. So basically Sentinel-1, 2, and 5P are the ones I'm interested in when I want to better understand volcanic activity. And I'll give you now this graph, which basically it gives you an overview of what you'd expect to see at what kind of time of a volcanic eruption. So here in the middle, you can actually see the seismic activity around the volcano, and here the eruption starts, but you have like quite low seismicity at before the eruption actually happens, and then right before the eruption you have quite high seismicity, as there's loads of stuff happening underneath the ground. And as soon as the volcano bursts, the seismicity is quite high again, but then it kind of like decreases after a time. So now when we look at the first information on this graph here, that's related to ash. So when are we actually able to look at ash when an eruption happens? So that's usually, or actually always the case, that you can look at ash as soon as the eruption happened, depending on what kind of eruption it is. But if it's an explosive eruption, you'd expect ash to be emitted when the eruption starts. When it comes to gas, that depends on whether the volcano is active or an open or closed volcanic system. If it's an open volcanic system, this means that it is passively degassing throughout the whole time, even if there's no volcanic eruption. And if it's a closed system, you'd only just expect emitted gases when the eruption starts and throughout the period of the eruption. So this means that if we are interested in gases, we could actually use satellite data, and this means like ultraviolet or visible light or infrared in order to look at gases prior to the eruption, during the eruption, and after the eruption. When it comes to hotspots, or which basically means any kind of lava flow or dome growing activity, we would use infrared tools which are able to look at infrared wavelength, and we'd expect this to happen shortly. We expect to see signals in here shortly prior to the eruption, or generally after the eruption, or like obviously also during the eruption. And when it comes to radar satellite data, this is actually used to look at the formation of the volcano, which means like whether the volcano is uplifting or subsiding. So this means that you would actually expect some kind of deformation signals throughout the whole time of the volcano. So it's either, so prior to eruption, the volcano could inflate, and then the eruption would start. You wouldn't really be able to see anything because there would be lots of noise in the data, but then afterwards you would expect the volcano to deflate. So that's the case for 50% of the volcanoes, that you would actually be able to see exactly this pattern. I'll come back to this in a bit too. So the first volcano, the first satellite mission we'll be now looking into is the Sentinel-5P satellite. And this is actually used for air quality monitoring, as well as like looking at the ozone layer or methane in the air. So this is basically used for climate modeling and forecasting. And within this satellite, there is an imaging spectrometer which covers wavelength between the ultraviolet spectrum and the short wave infrared, as you can also see at this graph here at the bottom. This Sentinel-5P satellite is actually like a passive remote sensing tool, which means it measures the solar radiation reflected by and radiated from the Earth. And this at the top of the atmosphere, which means if there is no sun radiation, you can't really detect anything because there's nothing the satellite is able to receive. If you look here onto the launch date, that was in 2017. All of those satellite missions from Copernicus, I think they started someone like 2014, someone around those kind of years. But generally, in order to use satellites for like scientific reasons, this is actually a very new thing. So if you have ever heard in media that maybe volcanic activity increased in recent years, that's actually more because there are more tools available to actually look at volcanic activity. Which does not mean that back in like the 50s, when we didn't have any satellites to look at volcanoes which are really remote, there was no activity. It basically just means that there was nothing to actually detect it. So back to Sentinel-5P. In order to look at volcanic activities, we'd be here interested, for example, in how SO2 is distributing after a volcanic eruption. And this is the example of Etna in February and March this year. So actually just a couple of weeks ago. And here you see a cloud of sulfur dioxide, which is distributed around southern Europe. And it depends on what kind of wavelength you're looking at. And here it's like the ultraviolet spectrum is selected, and this enables you to actually look at this sulfur dioxide cloud, and that's the same here at Raikoke volcano. That's a volcano in Russia that's located here. So this is like Japan, and that's like Russia all over here. And here you can see processed satellite imageries which were put together in a GIF, so you can kind of like understand the distribution of this sulfur dioxide. Actually, so now you might wonder why this is actually relevant for us. Why do we want to look at this data? So apart from the fact that it's important for human health, and we need to know whether we're exposed to any hazardous gases, it's also really, really crucial to aviation, as volcanic gases, but also ash, can be very hazardous for airplanes. I'm not quite sure if you can remember, but 10 years ago, in 2010, there, I think you probably were about 7 or 8 or so. There was this eruption in Iceland from Eyjafjallajökull, and this actually caused the whole of Europe to pause with any kind of airplane activity, which was a really big economical issue. So therefore, it's also very, very important to actually track those clouds and better understand where they are, so we know where planes can actually go in order to not crash, in order to not have their engines broken by those gases and ash. So when we come to Sentinel-1, this is a 2-satellite mission. Each carries an advanced radar instrument. And this is an active remote sensing tool, so it's sending and receiving microwaves. And this is actually enables all weather and day and night imagery. And when we are thinking of what we could use this for volcanic monitoring, this is usually used for volcanic displacement signals and deposits. So back to this volcanic deformation I mentioned earlier already. So prior the eruption, you'd expect the magma reservoir underneath the volcano to be filled by material from the lower crust or the mantle, and this is causing pressure, and therefore the volcano is uplifting, and it's uplifting as long as until it erupts, and then after this you would actually expect like a deflation at the volcano again. And this is actually where SAR data is really relevant, because you'd need to imagine those radar waves being sent to Earth from the satellite, and they are kind of like reflected back to the satellite again as soon as they hit the Earth. And if you have this one image of the received of the sent and received wavelength, and then you pass by 6 days later, then like the satellite passes by 6 days later, and this wavelength is actually getting shorter, this means that the ground is coming towards the satellite. If the wavelength is getting longer, this means the satellite is going away from the satellite. So if the ground is coming towards the satellite, this would mean an uplift, and the other way around. So dependent on what kind of magmatic source we'd expect, we also expect different kind of deformation patterns. And for example here, if we look at the scale, meaning from red to blue, it's 3 centimeters of displacement. This means if we go from this red area to the next red area, that's 3 centimeters, and then there is another red area and another red area. So if we look at this image, we'd expect around 9 centimeters of uplift. Exactly. And now I have an example for you. So that's Tal volcano. This volcano erupted in 2020, so last year, and it has this really, there are like so many of those fringes, as they're called. And if I'd love to like go through it with you now and kind of like count all the fringes, but actually they're really getting really tight the closer you get to this volcanic lake and the actual volcanic island. So I've included this image too, where they kind of like calculate the whole displacement. And here you can actually see this area around the volcano uplifted for 52 or like actually 53 centimeters, and deflated on the other side of the volcano for about 44 centimeters. And what is also really exciting is that if you look here at the date, you see that there is a difference of 6 days. So this whole uplift and deflation of actually over half a meter happened within this 6 days period. We can't really say from like only just the satellite imagery when exactly it happened. We can only just say it happened within this 6 days. So in order to like define it more accurately, we then go back to like ground-based measurements again. So the last satellite I want to talk to you about is Sentinel-2. That's also a satellite mission. It's like optical imagery, and it images the Earth with 13 different spectral bands, and they're used in order to track land and vegetation health. And this is the same as Sentinel-5P. It's also a passive remote sensing tool, and here you can also see the different bands which this volcano is receiving. This is the atmospheric transmission. So when you see this curve in the back is high, this means that it is able to propagate through the atmosphere, and the satellite is actually able to receive this wavelength. And for us, the short wave infrared spectra is really important, and this band of 12. I'll come back to this in a second when we look at the exercise I prepared. So if you look at this case study here of Etna, also in February, we see that this is a true color image, basically an image your camera or your phone camera you could take too. And this is a false color image where we've selected the band 12 in order to be red, because it's a red, blue, and green image. So since it's selected red and this infrared wavelength is able to detect the heat of the lava flow here, you can really nicely see the lava flow in this image. The same counts for this one. So as I mentioned before, I thought it's really interesting probably to look at how we are actually able to access this data, because there are so many different platforms, and since Sentinel, since Copernicus data is freely available for all of us, we'll quickly open this. And here we would go, so that's the Sentinel Hub, and we'd go to the Earth observation browser and start exploring. I've prepared this website already because now I need to log in and kind of like search for the location. So I've opened that already before. And this basically is Etna at the beginning of February with a true color image, and you basically can't see any lava flow. So this now would actually mean, oh, there was no eruption yet, kind of, or like there's just no lava flow yet. And if we then go, if we then go to the next image, if it would load, it hopefully does. So here we do have the same situation. We look at the lava flow, we look at the volcano, and we also have this true color setting, which basically means it's like an optical image, which we'd be able to see with our eyes too. But this is actually a date which is like the 26th of February, where the lava flow should actually be visible already, but we still can't see it here. So this basically means that the bands we selected here are not able to capture the lava flow. But if we change to a band setting, which is including band number 12, this would actually enable us to see a lava flow. And if you zoom into this, you can nicely see the lava flow in red and all the craters too. And actually now if we go back to this imagery where there was no lava flow yet and change the bands too, we still can't see a lava flow, but we can see nicely the craters of Etna. So that's very exciting here. And if you're wondering what the blue area is, this is basically all the ice cover around the volcano, and then the green bit is the vegetation. Because if we now go on to customize, which basically means that we can choose any of those different bands here, which are captured by Sentinel-2, we could say, let's give red color B12. This is the shortwave infrared band, and then green B11, and then blue B4. This is the image we were just looking at, where you can actually see all those colors you were seeing before too. But if we now decide to give, for example, blue, kind of like set blue as B12, this would then mean that it's changing in the ways of like that the lava flow is now actually blue. It doesn't really matter what kind of which band you assign to which kind of color. It's more that humans are more kind of, for us, red usually means hot, and therefore it's quite often the fact that like this infrared band is just assigned to red just because it's easier for us to understand. So actually, if you look at this image now, that's the 3rd of March, so a couple of weeks ago. That's where you can see the lava flow the nicest. And this has also this setting I was talking about already. And I've also prepared this one where you can also look at the status if it's loading. That's also always an issue because it's such a big data that it sometimes just needs a while to actually open properly. But yeah, you could kind of like select those images with the pin and then compare them with each other. And this is what I've done here. And now we can, well, you could switch between the two imageries and look what actually changed. And you can kind of like extract the information out of this regarding how far the lava flow went and like how much deposit, how much material came out of the volcano and all that kind of information, which can be really useful in order to mitigate risk. So, and after that, I'm coming to my last slide of my presentation. I hope you'll find this of any interest, because I thought if you now think this topic is really interesting and you'd like to maybe also go into this field, I thought I'd give you an kind of like show you how I got here doing this PhD in remote sensing and volcanology. So basically started with doing a bachelor degree in geography back home in Vienna at the University of Vienna. And then during this time, I was able to do an exchange semester in Italy. And as I had to do internship throughout my bachelor degree, since I was in Italy already, I decided why not keep on doing this, and decided to do an internship at the ENGBU in Naples. So that's basically the local research centers in Italy at the Volcano Observatory of Vesuvius. And during this time, I had a chance to kind of visit, I mean, obviously, Vesuvius is not active at the moment, but I had a chance to visit Stromboli and Etna, and I was really fascinated by looking at those active volcanoes and what information I actually can gain out of those volcanic activities, that I decided to do a master's degree in volcanology. That's the first time I actually moved to the UK, doing it in Bristol. And then I did an internship at the German Research Center, where I actually first got into touch with satellite data and using it for volcanic activity. And this actually led to the fact that I applied for a couple of PhDs. I think it was like 6 in total, and got this very last this PhD, which I'm doing now. So that was my talk. I hope that was in time. I think we have another 10 minutes, right? So thank you very much for listening. I hope you found it interesting, and I'm happy for any questions you might have now. Oops.
Hi Eva, I've got a couple of questions that I've written down to begin with, and if my students have got some, they'll pass them on to me. But first of all, so you mentioned about the deformation and the ground uplift, and then the inflation and deflation. How sensitive are the instruments? What sort of change are they able to detect?
They're actually able to detect a couple of millimeters. They're very, very sensitive. I can't really tell you the exact like range, but they're like able to detect like 2 5 millimeters already. So that's very, very sensitive.
Wow, and am I right in saying, you might know this better than me, but the sorts of figures that you were talking about up to a meter. I seem to remember when I first was teaching and we used to use Mount St Helens as an example. The inflation on the side of Mount St Helens was massive compared to that, wasn't it? It was measured in meters, wasn't it? Have I got that right?
Yes, I think so. I don't have the numbers in. I can't tell you the numbers at the moment, but I mean, like, even this Tau volcanic eruption I showed you before, that has like a displacement of like 50 centimeters in just 6 days. But as much as I can remember, the Mount St Helens eruption, this activity built up for over quite a long time. So if there is a really large time span where like magma is just kind of like the magma content in the crust is getting bigger and bigger, let's say, there's just so much time to actually build up such a big displacement that you could definitely reach a couple of meters when it comes to displacement.
Wow, thank you. Also, on the presentation, there was the Space Hub Yorkshire logo. Some of our students might be interested in that. It's not something that I've ever seen before.
Absolutely. Thanks for reminding me. I should have definitely said that at the beginning. So the Space Hub Yorkshire is basically, how do you say that? Not an organization. We kind of like came together to make the space, any kind of like space-related jobs and research, kind of like publicize this a bit more and like bring it into the world so that people actually have an idea of what kind of jobs there might be, or like what activities there are, like what kind of like companies in Yorkshire there are which are actually working with satellite data. There's for example a company based in Leeds with a couple of researchers from the University of Leeds too, which is called SatSense, and they are using satellite data to exactly do this ground deformation work. And if you want to know more about this, there is a Twitter page, for example, which is also called Yorkshire Space Hub, where you can get more information about any kind of like news related to satellites, not only just the region of Yorkshire, but generally also covering topics like ice sheets in Antarctica. And yeah, I think we don't have a website yet. It's about to we're about to like build this website now, but yeah, it's basically a way where we are trying to get more people interested in volcanoes. Not volcanoes, satellites. Satellites, that's what I want to say. Volcanoes are very interesting too. So, yeah. Superb,
thank you. Some of my students are just writing down some questions. I'll just wait for them to pass them on to me, and then I'll send them your way. But yeah, that's great. I'll put a link on our Twitter at college to Yorkshire Space Hub as well, if that's okay.
Yeah, absolutely. Also, if you want me to share this, I don't know, would it be useful to copy something into the chat box here, or should I just email you? Because I kind of thought it might be nice to, so this there is a quite long tutorial about what you can actually do with Sentinel Hub and how to analyze lava flows with Sentinel-2 imagery. Would you be interested in kind of like using this tutorial? I can email you, but I also just put it into the chat box if this is useful.
Thank you. Yeah, if you could email it as well, that'd be brilliant. So one of the questions, Eva, and I'm just a bit conscious of time because our students are going to be leaving in a couple of minutes, but one of the students has asked, how do the Sentinel satellites that you mentioned get put into orbit?
They're basically put into orbit with a rocket, and so you need to launch this rocket and then kind of like aim to put it into one of those orbits. It needs, and then also needs to have the right speed in order to kind of actually stay in this orbit. This can actually mean that it has to have a speed of like 7 point something kilometers per second, that it actually is able to work within all this forces within the space, that it actually stays in the orbit and does its job. And they're like powered with solar panels, so they're actually able to work up there for a long time.
Awesome, thank you. And the last question that we've got is, when you were showing us the images of the ground uplift and deformation that was going on, did it cause damage to the local infrastructure?
Absolutely. Absolutely. This is a big. This is actually also a reason why you don't only use those kind of satellites for. You don't only use radar in satellite or like imagery for looking at volcanoes. It's also very, very important to, if, for example, as a Mexico City, they kind of like take loads of water from their groundwater resources, and therefore the whole city is subsiding, and therefore you have loads of cracks in buildings, and this is leading to like building instability. And this is also a big research topic actually. So yeah, it definitely influences buildings in that kind of way.
Marvelous, thank you so much. That's been fascinating, and I'm sure there are students here who will really want to follow up on many of the things that you've discussed there. So thank you.
Yeah, I hope this is interesting for you, and I hope some of you might consider going into this field. This would definitely, like, there's so much data out there, and we just need people who work on them. So this would be exciting.
Fabulous, thank you so much, and have a wonderful rest of the day.
Thank you for listening and all your questions. Okay.